Hi everyone, I am Muhammad Danish Kashri and today our team is presenting the design and simulation of two-stage amplifier circuit. I'll be walking you through the schematic diagram. As you can see on the screen, our entire circuit is powered by a single 15V DC supply, VCC at the top. On the far left, our input V signal is set to an AC waveform of 10 mV peak at frequency of 1 kHz, which passes through a 600 ohm series resistor. The circuit is divided into two main amplification stages. Stage 1 is common source amplifier, utilizing a MOSFET labeled Q1. The DC bias for this MOSFET is set by voltage divider network using RG1 and RG2. We also have our drain resistor RD and our source resistor RS. A critical component here is the bypass capacitor C3. By properly connecting C3 in parallel with RS, we short the AC signal to the ground, completely removing negative AC feedback and unlocking the maximum voltage gain for this first stage. The amplified signal then travels through our interstage coupling capacitor C2 and enters stage 2. This is a common emitter amplifier built around a BJT labeled Q2 for this simulation. We specifically configured the BJT with a beta of 350 meet our design parameter. This stage is biased by resistor 1 and resistor 2, with the final amplified signal passing through our output coupling capacitor C5 directly to the 20 kilo ohm load resistor. The coupling capacitors C1, C2 and C5 are crucial because they isolate the DC bias voltage of each stage while allowing the AC signal to pass through seamlessly.
Hello everyone, I'll be walking you through our DC analysis part, and for this part, what we are going to do is that firstly, we simplify our circuit by short-circuiting all of our capacitors, and here we've obtained two parts, which is our MOSFET and also our BJT. So for our MOSFET part, what we do is that we first use voltage divider rule to obtain our VG, and once we do that, we substitute VG into our KVL and obtain our ID. Then, given the formula ID equals to K bracket VGS minus VT squared, what we do is that we substitute our given information and then we find our VGS. So we'll get two options for VGS, but we only take into account the positive value. And then what we do is that we substitute into our main equation VCC minus RD minus VDS IDRS equals to 0, and we are able to obtain our value for VDS. Then for part 2, we also use our voltage divider rule to obtain VTH, and once we do that, we substitute into our KVL and obtain IB. Now given the equation of IE equals to IB plus IC, and we are also aware that you're able to form another equation since beta equals to IC over IB, so IE would be equals to 351 IB. And then what we do is that we substitute all the relevant information, and we're also able to obtain IC as well and IE. Then what we do is we form our KVL, which is VCC minus VC minus VCE minus VE equals to 0, and we are able to obtain our VCE. Then VE equals to VCC minus VC minus VCE, and we are able to obtain our VE. And for our final step, for VC naught equals to VCC minus VC, substituting all the relevant information, we're able to obtain our final answer, which is 13.505.
Hi everyone, today we're looking at the AC response of this two-stage amplifier circuit. We are injecting a small 1 kHz AC signal at the input and measuring the amplified result at the output load. Now let's take a look at the transient analysis. The red trace is our input signal, Vin. If we look at our cursor data, you can see it has a tiny peak voltage of exactly 9.9745 mV. The green trace is our amplified output, Vout. Our cursor shows a peak of 63.4873 mV. By dividing the output by the input, you can see this circuit is giving us a voltage gain of about 6.365. Notice how the peak of the green and red waves align perfectly because both amplifier stages invert the signal by 180 degrees. Our final amplified output is completely in phase with our input, and that is how we analyze the AC waveform of a cascaded amplifier.
For the AC analysis, first we need to draw the small signal hybrid pi equivalent circuit. This is the circuit, and as for the values inside the circuit, we can see on the left, which is the RBB1, RBB2, IDIC. Then we also need to calculate GM1, GM2, and R pi. These are the values calculated. Okay, now we move on to Z in 1, Z out 1, Z in 2, and Z out 2. We can also get the values shown here. Now we move on to the gain calculation. For AV1, which is at the MOSFET side, we know it's V out over V in, and these are the calculated values, and in the end we get negative 7.981. AV2 BJT side, same formula. Is only the calculation part is different because of the RE1. So the value calculated is negative 1.917. Total gain is the product of sum of AV1 and AV2, which is 15.3. AVS is the same, it's just AV times Z in 1 over Z in 1 plus R sine, and we get 14.971. And that's it for the gain calculation.